a shot at. We'll get to that with some work on Monday and Tuesday. We'll finish all this up, but I put all the practice problems in this one packet. So this is, we're done with the pink except for this. This is cool. Law of exponential change. You may or may not have heard the definition of exponential functions in this way. Let me show you something. Have you ever heard? There's something fun about exponential functions. Okay, some b to the x, and often it's e. E is our favorite exponential function. With Euler's number, Euler's a popular fellow. Euler's number, that's what e stands for. And we're doing Euler's method today. It's like Euler day. Watch this. When you go to a particular height on that function, let's say here, let's say it's 5. Okay? If I go to this spot right here, let's say it's 10. If I get a slope of a tangent line back here, and if the slope here happens to be like 15 on that one, the slope on this one up here, do you want to know what it's going to be? Does anyone have an idea what it might be? It's got a fancy little deal with it. $30. Okay. Exponential functions have this really cool property. The slope of the tangent line is a constant multiple of the height that it's at. Oops, that's not what I wanted. Undo that yellow line. I wanted to highlight in yellow. Try that again. Check this out. If I'm at a height of 5 and my slope is 15, that means my slope is 3 times bigger than my height. That means if I go to a height of 10, my slope's going to be 3 times bigger than my height of 10. If I go to a height of 100, way up here, meant to hit red. If I go to a height of 100 right there, then the slope of that tangent line will be 300. So it's always, what's cool about an exponential function, every slope of the tangent line is the same constant multiple of its current height on that function. And it's not for any magical reason. We'll find out here in a minute where that comes from when we do some differential equations on it, but that's where this little equation, that's what this says right here. This says in an exponential function, the slope, which is what that equation of the tangent line, is just a multiple of whatever your y value is for any given x. Super cool. So let's see how that proves out. Let's do the mathematics to justify it a little bit. And I just love that definition of it. I just think it's so neato. Got to get my eraser a little bit bigger. Okay, and I'm going to write in pink again because we need more pink. Let's go for it. So, hey, there's a differential equation. Let's go solve it. Okay. So we put y on the right and the left. Couldn't get the dy in there. I'm sure you're all happy. Is that? Okay, we separated variables. Y's on the left, x's on the right. There were no x's, so I left k over there. Log, a natural log, and it's used absolute value. Let's leave the absolute value today. I don't think I talked about that yesterday, and we probably should. And that's kx plus c on this side after integration. Okay, remember I integrated. And we eat up. Eat up. And what happens, that cancels the log, and you get the absolute value of y is e to the kx plus c. And we found out yesterday that that plus c, it means to multiply by e to the c. And that itself is a constant. So what we were able to do is get it down to this thing. Now, I'm going to eliminate the absolute value. When you eliminate an absolute value, you get this nice, you can deal with this plus or minus piece in here. Okay. So what happens is In an exponential function, the y, exponential functions by their own nature, when I'm looking at it just here at this step, usually when you take the log, you have an absolute value in there, and it is essential. But do you notice in this little highlighted section right up here, an exponential function like the one we're seeing right there, they're always positive. They're always above the axis. So the absolute values aren't necessary. When we remove them in some other problems later, we'll have to put a plus or minus in there because we could have one or the other that would be possible in there. But for this problem, we always know the exponential is going to be positive. So I dropped it yesterday and I didn't really talk about it. So just so you know, sometimes the absolute value is really important. We have to put the plus or minus. For an exponential, it isn't. But look at that. So here's what this says. Hey, wait. That means for this differential equation, these two are very much related. The derivative of any exponential function results in simply a multiple of our y value. If you go back and do that. So we did the antiderivative that got us here, and if we take the derivative back, we'll just always get a multiple of y if you take that on. It's just a fun way to look at derivatives, kind of reveal properties and behaviors about this. Okay.
So it's dy dt at the top.
Yeah, did I throw out the t? Yeah, just t. Just change all those to t if you want in there. I love, yeah. But that's our input variable. Yeah. Cool. But other than that, yeah, you're seeing that multiplicative nature of that in that derivative. Okay, you get to memorize it. See? Memorize. 3 times the charm. If you get dy over dt is ky, some multiple of y, then you can instantly say, oh, it's one of those exponential, ce to the kt. You can just go with it, and you're good. And you want to know that. Here's how. Go down to the bottom. I'm going to give you guys a challenge. It's a fun challenge. So this first population, example 7, I go from 400 to 1600 in 3 hours of bacteria, just a regular day with bacteria growth. Gotta love that stuff. Assuming that the population grows according to this rate Kp, where t is in hours, find the value of k. So I'm going to give you a little hint. If I say dp over dt is kp, your brain goes, oh, I got this. That means p equals ce to the kt. Instantly, like you know that's your antiderivative without having to go through all the work to get it. Since we have a couple values, I want to put something down here, a little system of equations. I'm going to challenge you to find, what if we knew it went from 400 to 1600, so when I had a population of 400, okay, ce to the kt, right? Then it went to 1600, which was 3 hours later. I'm going to ask you to try and figure out what k is. And I'll tell you there's a shortcut later, but I want to see if you can justify it. There's a shortcut that always bothered me. I was like, I didn't get it until this situation. So you and your mates, your challenge at this particular moment before the shortcut is solve for k and tell me what k is. There's enough information in there. There's 2 variables, 2 unknowns, c and k. It can be done. Solve for k. Have fun.